Hello everyone. Today we'll be talking about calcium-ion batteries, a type of battery that could be a cleaner, safer, and more affordable option in the future. So this presentation will cover why calcium-ion batteries are being explored, their advantages and their challenges, and what progress is being made to make them better. So let's first look at why calcium-ion batteries are important and getting attention. So first reason is calcium is cheap and available. It's the fifth most common element on Earth, which means it's much cheaper than lithium and easier to find. Second is good energy storage. Calcium can store almost the same amount of energy as lithium, so we can expect strong performance, especially for things like electric cars or backup power. And third is better safety. Calcium has a higher melting point, so it can withstand heat better than lithium. It also forms fewer dendrites, which are tiny spikes that can cause battery failure or fires. So overall, calcium batteries are safe and more stable. So the next slide is we'll discuss about key challenges in calcium ion batteries development. So even though calcium ion batteries have great benefits, they are still under research and have some major technical challenges that to be resolved. So the first challenge is calcium ions are large and slow moving. So what does this mean? So compared to lithium, calcium ions are bigger and heavier. This makes it harder for them to move quickly through the battery materials, which slows down the charging and discharging process. As a result, the battery may take longer to charge and may not deliver power efficiently. The second challenge is electrolyte incompatibility. The electrolytes used in today's batteries don't work well with calcium. They tend to form a passivating layer on the surface of the calcium, which blocks the ions and prevents smooth operation. This reduces the overall efficiency and life of the battery. And third challenge would be electrode material issue. The materials used for storing calcium ions, especially the electrodes, are still not good enough. Many of them can't hold and release calcium ions easily. This causes problems like poor energy storage, low efficiency, and shorter battery life. And the last challenge would be unstable SEI layer. So what does SEI mean? SEI stands for solid electrolyte interface. This is a thin protective layer that forms on the battery's anode during use. In calcium batteries, this layer is still not well understood, and it can lead to instability or weakness. If this layer breaks or becomes too thick, it can cause the battery to lose capacity quickly and become less reliable over time. So our next slide will be on anode material advancements. To improve calcium and batteries, researchers are focusing on better anode materials. The anode is the part of the battery where calcium ions go during charging. Choosing the right anode is very important for performance and other parameters such as safety and power. So we'll study three types of anode materials. The first type is metallic calcium anodes. These use pure calcium metal. They have a very high capacity, which means they can store a lot of charge. However, they also have serious problems. Calcium metal can form thick layer of passivation, which will block ion flow. There is also a risk of dendrite growth, which can cause short circuits and damages the battery. The next type is alloy anodes. These anodes are made by mixing calcium with other metals such as tin. These materials have shown stable performance in lab tests. They allow reversible reactions, which means the battery can charge and discharge many times without any loss. They also help in the reduction of passivation problem, making the battery work more smoothly. Third type is graphite intercalation anode. Graphite is already used in lithium-ion batteries. In calcium-ion batteries, the calcium can be co-intercalated into the layers of passivation with some solvent molecules. These anodes have a lower capacity, so they don't store as much energy, but they are very stable and safe. That makes them a good choice for long-lasting batteries, even if they don't provide the highest power.
Hello everyone. Today I'll be briefly talking about the recent progress in calcium ion battery research focusing on cathode materials and the electrolyte development, especially in the context of making these systems more viable and scalable alternatives to the lithium ion batteries. Firstly, let's start with the cathode materials which play a critical role in determining the performance of the calcium ion batteries. Firstly, vanadium based materials have shown the most promise. Their open framework structures allow allow for reversible calcium intercalation. For example, hydrated vanadium oxides can maintain over 90% of their capacity even after thousands of cycles. This is because their structure helps in accommodating the larger calcium ions efficiently. Next, we have organic cathodes, particularly quinone-based compounds. These materials offer tunable redox sites and excellent structural flexibility. They have demonstrated good stability across extended cycles, over 2000 in some cases, though challenges remain in achieving high voltage and long-term stability. Lastly, conductive polymers like polyaniline and polypyrrole are being explored. Their inherent conductivity and flexibility help in enhancing the overall electrochemical performance. These are particularly promising in enabling calcium ion insertion without compromising capacity or cycle life. Moving on to the electrolyte development, this is one of the most critical areas in calcium ion battery research because calcium metal reacts readily with conventional electrolytes, forming passivation layers that block ion transport. There are four major types under research. Firstly, being non-aqueous electrolytes, which are optimized to enable reversible calcium plating and stripping at room temperature. These are essential for making the system rechargeable. Second, being organic solvent based electrolytes, which are effective in dissolving calcium salts while maintaining a stable interface with calcium metal. For example, using solvents like THF has shown reduced passivation and enhanced reversibility. Third, third one is ionic liquids, which are gaining attention due to their non-flammability and broad electrochemical stability. These are particularly helpful in high energy systems because they maintain stable calcium electrolyte interfaces. Fourth one, and finally, solid state electrolytes are ideal for safety. They eliminate flammable solvents and improve mechanical stability. However, their low ionic conductivity and poor interface with calcium metal are still major hurdles researchers are trying to solve. This brings us to some of the most exciting recent breakthroughs in solid-state electrolyte design. The first is calcium hydrodoborate. This material has shown high ionic conductivity at room temperature, which is at the scale of 10 raised to minus 5, which is a big step forward. About the soft lattice structure and the inclusion of methylamine ligand helps in making calcium ion transport easier and more efficient. The second major breakthrough is the monocarborane based solid electrolyte, namely calcium monocarborane. This material has a unique cage like molecular structure that enables excellent ionic mobility while maintaining a stable interface with the calcium metal. Importantly, it resists forming the thick layer passivation layers that hinder performance in the most other systems. Both these materials offer new hope in addressing the long-standing issue of poor interface compatibility and low ionic mobility in solid-state calcium batteries. Calcium ion batteries may soon transform from a research concept into a real world solution for sustainable energy storage. So, this was all about the solid state electrolyte breakthrough and other key points. Thank you.
The next slide is basically these slides talk about the three major challenges that happen at the interface of the battery and electrolyte, which we must solve to improve our battery life and safety. The first layer is passive layer. This is like a thick crust that forms on the battery. It stops the ions from moving, so energy cannot flow easily. This is basically reduces how much charge the battery can hold. And the next is irreversible plating. Here, some calcium gets stuck and they cannot come back. That is called as a dead calcium. It wastes a part of battery and reduces its lifespan. Next one is dendrite growth. Think of small sharp branches growing inside. These can rise through layers and even causes us some short circuits which causes damages which are more dangerous. Basically this slide shows why calcium is promising material for future batteries. It has a great performance potential and practical advantages. And here basically this graph shows about the high capacity, high melting point and abundance. First, high capacity. High capacity is about 2073 milliamps hours per cubic centimeter. That means they can store a lot of energy in a small space, making them ideal for high performance batteries. High melting point, about 842 degrees Celsius. Calcium has much higher melting point compared to a lithium. This makes the battery more stable at high temperature, improving the safety, especially important in electric vehicles or a large power storage. And the next is abundancy. Abundancy and rank 5 in earth crust. Calcium is the fifth most abundant element in earth crust. That means it is easy to find and cheap to extract, making a calcium batteries more cost effective and sustainable in the long run. And basically, this chart shows how performance matrix or related materials properties have been improved over time, pointing to a calcium's growing potential in energy storage. So overall, calcium offers a high energy storage, safety, and affordability, making it a strong candidate for the next generation batteries. In order to improve calcium ion batteries in the future, researchers are focusing on a new materials, smart computer simulations, better monitoring, and smarter battery designs. And here the future perspectives for CIBs. The first is advanced material design. Scientists are using a battery materials like a phosphate-based cathodes, adding a tiny amount of other elements called doping, and here applying a special coatings. These steps can make the battery work longer and more efficiently. And the next is computational modeling. We also use the computer simulations in order to understand the calcium reacts and which it moves inside the batteries. This saves time and money in the lab by predicting a behavior before real experiments. And the next is in situ diagnostics. This means watching the battery in a real time while it is working. Basically, it helps to see what changes happen inside a battery and find the problem early. And the next is electrolyte and electrode architecture. Innovation designed like water-in salts, electrolytes, and smartly sharpened electrodes help batteries work better and safer. These new structures improve energy storage and charging. Basically, this picture shows the researchers working in advanced labs to develop and test these ideas. This is all about the future perspective for CIBs. Thank you.